Now let's solve it for a little bit longer. And let's plot this as blue. Okay, so here what we see is that the solution is actually still goes wrong. It's better than the finite difference solution, right? But still, it's not doing what it's supposed to be doing. It's not actually capturing the discontinuity without creating oscillations. So what do you think is wrong here? What should we blame? Yes, interpolation, right? So if we have actually a discontinuity, okay, interpolating between the discontinuity by taking an average does not seem to be the most bright idea, right? So especially if you think of a discontinuity that may actually not lie exactly on may not exactly lie on the boundary of two volumes. So let's imagine I have one volume that is over here, another volume over here. I have a cell average over here. I have a cell average over here, right? Okay, interpolation is going to give me a value that is kind of over here, and for burgers, a value over here means I don't have any flux, right? Okay, I have very little flux. So now, if I have a very little flux, so let me say this is 1 and this is -1, which is actually what we get when the two peaks of the curve collides. So I have a flux over here that is equal to half. I have a flux over here that is equal to half. And I have no flux over here. So how would the cell averages evolve in this case? Yes, there is more flux coming in this way, right? More flux is coming this way. And then no flux is going out on the right. All right? Okay, so that means the volume average has to keep increasing. Okay? While over here, there is negative flux, which means there is a flux on the reverse direction. There is flux going in from the right. Again, no much flux that is coming from the left or leaving from the left. So the value would further decrease. Right? So, okay, that seems to be not the correct way to do things, right? So any suggestions? How should we fix this? So what's different from what we did here and what actually happens physically? What is the flux? What is actually the flux across this interface? Half, right? Because the value of the function is actually equal to 1 here. So the actual flux is equal to half, while we, by this interpolating the function and then evaluating the flux way, we actually made a huge error, right? We made an order 1 error. Any suggestions to fix this? I'm waiting for your suggestion. There is actually a pretty simple thing to fix this.
Do you have the cell, do you have the shock sitting in the middle of the cell?
Oh, I can have the shock sitting in the mid. Can I have a shock sitting in the middle of the cell? Yes, that's possible.
Would that change it?
Would that? So what's your question?
So right now the two cells, the shock is near the edge of the two cells.
Yes. But I cannot control where the shock wave sits, right? So actually, if the shock wave is moving, then it has to actually move across the cell. So my scheme has to be correct wherever the shock wave is, right? So that's not out of my control.
Perhaps take the maximum flux and its neighbors.
Take the maximum flux and its neighbors. That gets, well, actually.
Might be zero.
Actually, now the central question comes to here, right? So as opposed to trying to approximate what the okay, so here there is a simple fix, that is as opposed to trying to compute what value of W it is here, why don't we directly try to approximate the flux, right? So if we evaluate the flux function on this cell and evaluate the flux function on this cell, we both get something close to half, right? So one of the insight in finite volume is instead of trying to approximate the solution and then compute the flux, it's actually a lot better to directly go for the flux. Okay, so in here I can show you if we directly go for the flux, as opposed to the interpolation of, let's say, of flux. So basically, we'll say flux is equal to W square over 2. And then interpolation of the flux, so we'll say Fi plus 1. Let me just say F. Right? And so now the Burger's equation is, definition is moved to here. And I don't need this anymore, and the flux accumulation is still the same, Fi plus 0.5, and this and this, right? Any errors you see here? So basically, I compute the flux on the cell average instead, and then we try to interpolate the flux. So now let's see what we get. We'll think, where is my plotting? We'll plot this, hold on, we'll evaluate this, and what's the difference between this and this? This. Okay, so now we see actually much less oscillations, right? There are still oscillations, but the oscillation has been tamed quite a bit. All right, so basically one thing we see is that we really want to directly approximate the flux as opposed to the do it indirectly. Okay, so why do we still have some oscillations? How do we further get rid of the oscillations? Higher order actually it's opposite to what we want, really. So basically here the problem happens near discontinuities. Okay, and near discontinuities actually what's actually the best interpolation scheme near a discontinuity? Yeah, piecewise constant interpolation that preserves the best behavior, right? So here the cause of oscillations, when you see oscillations like this, it's actually very similar to the Gibbs phenomenon. I mean, have you if you looked into Fourier analysis, right, you can know like you can write down what is the Fourier series of a Heaviside function, a function that actually has a discontinuity and otherwise is constant. And if you truncate the Fourier series to any level, you are going to see the Gibbs phenomenon. You are going to see near the discontinuity, you have undershoots and overshoots, pretty much something like this. So basically, it still has thing to do with the interpolation. That's right. So we are interpolating the flux, which makes it better, but we are still interpolating across a discontinuity.